Okay, I'm Melissa. I'm presenting a paper modeling distracted agents in crowd simulations. Crowd simulations are an important tool for analyzing for patterns in urban architecture and related areas. Historically, this work has focused largely on homogeneous crowds, so some aspects can be parameterized, but not all. Simulated crowds that include non-normative gates differ greatly from those that don't. Research shows heterogeneity in terms of emotion, cultural diversity, etc., has a significant impact on the overall crowd flow. Our paper takes the first step for modeling agencies and circles and crowds, which has become increasingly common in recent years and is now a significant safety concern in many urban areas, and so it's important for them to be included in analysis and visualization tools. A large body of research on distracting gates was reviewed and used to construct an early taxonomy of distracted behaviors, and then implemented in a state-of-the-art crowd simulation algorithm. The impact is then demonstrated both qualitatively and quantitatively through various crowd measures. The purpose is to demonstrate that simulated distracted agents have both visual and computational effects on the resulting crowd. One of many approaches to crowd sim are physical force-based methods, such as helping social forces, which use attractive and repulsive forces to guide the agent. Predictive force-based models also compute collision-free trajectories for a time window. One example is the predictive avoidance model. An overview of these and many other approaches can be found in Virtual Crowd's Steps Toward Behavioral Realism. It's been shown that including personality models like Ocean has significant impact on the resulting crowd. Decision networks have been used to simulate personal interactions between two agents with different personalities. Some navigation algorithms attempt to simulate vision without gaze. Rule-based perception models have been used to focus attention based on external stimuli. Other approaches simulate gazing crowds but do not investigate the impact of altered gaze due to distraction. One theory says that distracting activities can be cognitive, motor, or visual, or a combination of these. Another study showed that cognitive activities are usually the most distracting, followed by motor and then visual. We can imagine distractions as a taxonomy and break each one into categories based on cognitive, motor, and visual components, as shown here. Distractions are modeled as a separate layer above the steering layer. The distraction layer sends a message to the steering layer to change the locomotion parameters once triggered. Research suggests that pedestrians looking down at their phone rely on their spatial memory, proprioception, and peripheral vision to guide them to their goal, and this can cause them to drift left or right from their intended path, which is called lateral deviation, and they may also forget to turn where they're meant to. So to model this, we implemented a novel fuzzy goal model. So instead of heading straight for the actual waypoint, the engine heads towards a fuzzy waypoint randomly chosen from within some radius of the actual waypoint. The radius is determined by the distance to the actual waypoint when the engine becomes distracted. A raycast is used to ensure the point is reachable. We use the predictive avoidance model for simulating crowds, and we consider two types of distracting activities: texting, talking on the phone, and reading something on a smartphone. We modify the preferred speed, field of view, and labor distance parameters of the PAM algorithm and pass these to the steering layer along with the fuzzy waypoint if necessary. To set the desired speed, we use the default value of 1.3 meters per second for normative engines. We reduce this by 20% for testing engines, 18% for talking engines, and 12% for reading engines based on averages reported in the distraction literature. To set the field of view, we use a default value of 200 degrees for normative engines, and we reduce this by 7% or 186 degrees for talking engines. For reading and texting engines, we use a value of 48 degrees, and these values are based on studies from the distraction literature. So for labor distance, we used a default value of 10 meters for normative and talking engines because we assume that talking engines can still see as far as normative engines. For testing and reading, we use an estimated value of 1 meter. We set the fuzzy goal radius to 10% of the distance between the engine and the actual waypoint based on the highest values reported. No fuzzy goal is used for the talk on the phone behavior. To limit compounding factors, distractions are triggered at the beginning of the simulation and remain active for the duration. Now for the qualitative analysis. Blue engines are normative and red engines are distracted. Here we can see trajectories for a simple wall scenario, and we can see that talking engines have similar paths to normative engines, but reading and texting engines have wider turns and a little bit of backtracking when the engine passes the goal. So here we have a oncoming obstacle scenario, and we can see that the paths for normative and talking behavior are smooth, but for the reading and testing behaviors, we can see that there was a bit of a bump in the middle where the engines met. Here we have a surprise scenario, and we can see again the normative and talking behavior was similar, but for reading and testing, there were little bumps as the engines came around the corner. So here we have a diametric circle scenario, and we can see that reading and testing engines have some deviations and less smooth paths than the normative and talking engines. And the talking engines have even smoother paths than the normative engines, and that's because these red distracted engines move slower than the blue engines, so they reach the middle later, and this means there's less congestion in the middle. Okay, so moving on to quantitative analysis. So for quantitative measures, we use the flow rate, the number of agents divided by the total simulation time, the effort, the estimated total milliball energy expenditure over the path integral of all agents, and the kinetic energy, the total energy over the path integral of all agents. These are the formulas used to calculate these measures. So for the first experiment we use an Egress Scenario, and we can see the layout here. So we have the engines moving through a bottleneck towards the goal. We have 50 engines per trial with increasing proportions of distracted engines, and all distracted engines are homogeneous. The remaining engines are normative and use default parameters, and we have 20 trials for each of the 4 cases, with no distraction, with reading engines, with talking engines, and with testing engines. The mean and standard deviation are recorded across models and their proportions. Then we do a cross-school Wallace test, post-hoc cognitive test with false discovery rate and home corrections. And then we can isolate the significant differences between the models and the cross proportions. So here we can see some of the results. At the top we have a table for each of the different metrics that shows when the different models became significantly different from each other, or at what proportion of distracted engines in the crowd did the models become significantly different from each other. And at the bottom we have some graphs showing the different metrics for each of the models. Some key points were that testing has little impact on flow rate and effort, but does significantly impact kinetic energy when 20% or more are tested. Talking also had significant impact on flow rate and kinetic energy, and flow and effort may actually be improved in some bottleneck scenarios due to some engines moving slower and arriving later at the bottleneck, leading to less congestion. Okay, so then we did an experiment with a crossing group scenario with the layout shown here. So we have just 2 groups of engines going in the opposite directions. And we have pretty much the same setup as for the Egress scenario, but we also include high quality screen captures to highlight some results. So here we have some of the results for the crossing group scenario. At the top we have the tables for each metric showing the significant differences between models at different proportions in the crowd, and at the bottom we see the graphs for each of the metrics. So here we can see some of the trajectories of the engines. At the top we compare all normative to a case where there's 10 testing engines. And when there's testing engines we can see there's a lot more congestion in the middle, whereas normative is more smooth. And similarly on the bottom we can see that cases where there's normative or talking agents have a lot smoother paths than when there's texting and reading agents. So some key points were that as little as one agent talking or texting can significantly alter flow rate, and this includes reading at 2 agents and all models at 5. Models and distraction differ from each other after 2 agents, and distracted agents disrupt the laminar flow and increase flow rate and effort significantly. This was the first attempt at modeling distracted agents in crowds. The parameters are based on real studies and reflecting ground truth. Future work includes modeling more diverse sensory abilities and locomotion to improve fidelity and provide value in a number of areas. Now I will show some video demos.